this is a fuse, and a friend of mine lives in a reasonably old apartment building recently expressed his amazement he could purchase a circuit breaker type screw-in replacement for these, to which I replied rather flippantly, well, you could screw in a light bulb if you really wanted to, it just wouldn't make a very good fuse. That got me thinking about how bad of a fuse it would actually make. Seems like it's a really easy question to answer, but it's actually not. So it seems like this should be really easy, right? Because a light bulb is just a resistor. Well, a light bulb is a resistive load. It is not a resistor. It's actually a lot more like this metal oxide varistor, in that the resistance of the light bulb is going to change based on the voltage across it. That's pretty easy to demonstrate. This is going to be harder for you to read than just for me to read probably, but we know the operating characteristics of the light bulb already, as the manufacturer tells us. It's a 60 watt light bulb when it's connected across 120 volts. So if we've got 60 watts, we divide by 120 volts, it's going to be 500 milliamps. 120 volts divided by 500 milliamps should be about 240 ohms. But that's not what we're going to get if, for example, we connect a multimeter across it. The reason for that is simple. The multimeter is using a much lower voltage than 120 volts to measure this resistance. So since the voltage is lower, the resistance of the light bulb is lower. We can also demonstrate this with just a DC power supply. We're going to see as we increase the voltage, we are going to get a current, but if we work those out, 5.2 volts divided by 117 milliamps, it's even a different voltage than we were getting before on the multimeter, and this will actually glow eventually. I see it just starting to back there. That's about as bright as it's going to get on 30 volts, but even there, at 30 volts, 29 volts divided by 226 milliamps, we're only getting 128 of our ohms. So therein lies the complication of replacing one of these with one of these. As well, this has a fixed resistance, a very low fixed resistance, selected such that when it passes 30 amps of load, it'll melt. The resistance of this is going to depend on the voltage across it, which is going to depend on the current through it, which is going to depend on the resistance, which depends on the voltage. You see, we're kind of going in a circle here. So we're going to have to experiment a little bit and kind of see what happens. Alright, the setup here is relatively simple. I've taken this rig that I usually use for using my clamp meter with. I've just replaced the live wire with the two wires coming off the light bulb holder. So be able to plug this in, and then into this end I can plug in my, my poor man's Cliff Quick Test here, and I'll just be able to add different resistors in between the live and neutral. Turn it on. Should probably turn it off to start. Turn it on, and we'll be able to see what happens with the light bulb. And this is fused at, I think, 1 amp. Should probably find that out before I start too. This is fused at something, so that should be okay. Now obviously we're still going to be affected by is it Kirchhoff's current law? Somebody's current law. Anyway, the highest resistance in the circuit is going to have most of the voltage dropped across it. So if we try to connect anything that is lower resistance than this bulb would normally be at 115 volts, the bulb's going to drop most of it, and it's just going to be a light bulb with a resistor in series. So I'm going to start with resistances that are higher, significantly higher than this would be at 115 volts, so they drop most of the voltage. Now before I finish this video, I'm going to have to go scrounge some more resistors. This is unfortunately one of the only higher, relatively high power, high value resistors I have. 1.5K. Problem being, there it is. Yeah. 115 volts divided by 1500 ohms. It's going to be about 76 milliamps times the 115 volts. I don't think this 2-watt resistor is going to survive for very long, unless maybe the light bulb will have a higher resistance. Maybe it'll save it. I'm not too worried about doing this for a couple of seconds just to test it. I'll go find some more suitable resistors in somewhere. I had to swap for some meter leads that were significantly less safe, but a lot easier to grab onto something underneath there. So I'm going to turn this on, and hopefully we'll capture all the interesting flames. Interesting. We've got nothing. We've got about the 70 ohms that we expected the resistor to draw. But across the light bulb, we've only got about 2 volts. I'm going to turn this off. Oh, yep, there is smoke. I don't know if you caught the smoke. But there was some smoke. Resistor still looks moderately okay. Alright. Time to find some more resistors. Okay, I took the time to find some more resistors and also to think about this a little more, and I realized in retrospect, pretty obvious problem with this whole concept. But I already started making the video, and this process of connecting resistors across mains voltage has pretty high potential for entertainment, so why not keep going? Got a 100 ohm 10-watt resistor. This is a 510 ohm resistor from something, and this is a 330, and I've also found this resistance wire from when I thought vaping was cool, and a ceramic core to wrap it around. I can make my own resistor if I want to. Well, let's go. Okay, I've got the 500 ohm resistor, 510 ohm resistor in there. The obvious problem isn't likely to become more obvious just yet, but it will soon. Spared you watching me do this on the calculator. We should be getting about 225 ohm, or 225 milliamps. I'm going to bet it's going to be a little bit lower, just like before. Let's see what happens here. Is a little lower, just like before. We've got a little more on there. Oh, and there's the smoke. Alright, turning it off. This one didn't fare quite as well. I also didn't have enough leg on there, obviously, to hold it up off the wood, so the wood didn't fare as well either as the last time. Alright, the 330 ohm is in there. We're expecting 348 milliamps this time. Again, going to be a little less. I'm going to remember to turn on the backlight on here. Maybe you'll be able to see it. Yeah, a little better. Alright, here we go. Crackling. And the bulb is on. Ooh, smoke, lots of smoke. Alright. That one really didn't do too well. Ugh. And it stinks. Smells really bad. And we did see the beginnings of the problem, the bulb coming on there. Basically, as our resistance gets lower, we're essentially we're moving the light switch, right? We're moving where the live is actually connected. Eventually, if we went all the way down and just connected a wire, we just have a light bulb, you know, which isn't that interesting. But let's you know, let's put this in there. Why not? All right, I've got the 100 ohm, actually the 92 ohm resistor in there. You would expect 1.25 amps out of that. We're not even going to get anywhere close to that because, like I was saying before, we're approaching the wire, the 0 ohm link. The bulb is going to start just hogging all the current, and it's going to start limiting the current based on the resistance that it reaches as its voltage goes up. Let's watch. Yep. Now the bulb is, you know, pretty close to full brightness. 80 volts across it. Not seeing any smoke from that resistor yet. It's, you know, much higher wattage rating, and it's only got about 30 volts across it. Obviously, we're still not getting the draw that you would expect for that bulb because there's a resistor in series with it. The resistance is higher than it would normally be. Alright, let's just go full forward here. Got about 2.5 ohms of resistance wire. Let's see what happens. Got it just shoved through the ceramic core here. 2.5 ohms on 115 volts, for the record, would draw 46 amps. About, yeah. Or it would try anyway, and then the fuse in this would pop, and if the fuse in this failed, then the circuit breaker would pop. I don't expect any of that to happen. Alright, so it's clipped in. I'll turn this on. Remember, 46 amps is what we're looking for. Maybe I should switch to the 100 amp range just to be safe. And not showing up on 100 amps. Huh. So, can you use a light bulb as a fuse? Resounding no. But what we're looking at here is one of the other interesting circuit protection applications of an inline light bulb. It's going to limit the current to whatever the light bulb would draw. Because essentially what we've got in here, the resistance that I've got in there is a dead short, or close enough to it as far as the light bulb is concerned. So it's going to draw almost the 500 milliamps that it should in normal operation. And this resistor in here is only going to see 500 milliamps instead of the 46 amps that it would have otherwise. So if you have a circuit you're not too sure about, you're not sure if it's going to be a dead short inside or if it's going to go short while it's operating, put it in line with a light bulb that is rated at, you know, the current rating, above the current rating that the device requires. I've actually seen this on a couple of videos before. I just hadn't experimented with it like this. So I thought that was kind of interesting. And how's my DIY resistor? Well, it's fine, because this beefy DIY resistor only ever had about half a watt on it. Voltage was very low, around a volt. Almost all of the voltage was on the light bulb here. Just for extra potential for something to go wrong. Let's try it with some LED light bulbs. This one is, well, the outer part is from a kit. The inner part is yeah, that's a custom. This one's from the Dollar Tree. So this has a capacitive dropper transformerless power supply in it to limit the current. This, I believe these are resistive IC. I'm sure they'll both work, but let's see them work. Alright, I've gone back to the 100 ohm resistor, the 1.25 amp load. Not, you know, because I don't necessarily trust the handiwork of the Dollar Tree or myself, but it just seemed, you know, prudent. Nope, not hold. Backlight. Backlight on. Let's see. Yeah, we're getting basically the whole voltage across here. There's the voltage on our 92 ohm resistor. So yeah, it's clearly limiting the current a little bit for the light bulb, but the light bulb is doing most of the current limiting. It's also very bright. Alright, I didn't have any fusible resistors when I made this, so these are carbon film resistors, the inrush limiter fuse resistor kind of deal, so that has potential for some excitement. This needs the backlight turned on every single time manually. It's extremely aggressive about saving batteries, which is annoying because I've never had to replace them. Yeah, that's predictable. So this is limiting the current significantly more than the resistor is. And just for the sake of completeness, I've gone ahead and put the 46 amp resistor back in there, and yeah, exactly the same thing. Yep. So in conclusion, can you replace your fuses with light bulbs? Oh, no. But you can use them to protect your circuit if you have a circuit that you think might be failed short, or might in the future fail short while it's connected. Put a light bulb in series, and even if the circuit does fail short, no more current than would normally pass through the light bulb is going to pass through it. That's about... No, I'm just kidding. That's not just about it. Let's mount some resistors. There we go. Oh. Alright, that was 1,000 ohms, and it took a while to be really that interesting. So now let's try a 330. I've got the... I'm going to leave the fans on. It smells gross. Snap, crackle, pop. that has failed short. You can see the light bulb's on back there. It's kind of interesting. Thought it would fail open. Here we go with the little guy. Alright, 220 ohm carbon resistor. I think this might have the best potential for something exciting to happen. There, that was exciting. Alright, so there you have it. 4 melted resistors, no melted fuses or popped circuit breakers thanks to the inline light bulb. And that's the video.